It's time for everything. All right, so my, until recently, untitled talk is called Deploying the Graph. So this is part of the process we've been going through to modernise the way we manage our infrastructure. But let me talk a little bit about we. So my name's Kevin. I'm the CTO of a company called Playup. We're a startup based in Melbourne. We've been a startup for some time. We're still working on the revenue thing. And we're a mobile-first platform. So we do mobile applications around sport, on iOS, Android, and Windows. So let me tell you a little bit about us. We started off wanting to build up around engaging and entertaining around live sport. There's one question you can ask everybody in the pub. What team do you follow? You can't ask them something about politics. You can't ask them about their girlfriend, a whole lot of things. They're all going to cause you trouble. Or your boyfriend. They're all going to cause you trouble. But ask them about what team they follow, and you'll be able to do it. So we figured there was something there. We started out with that in mobile games. So about 4 or 5 years ago, we started off on a mobile games type thing, back before we had smartphones, and you could get those little Java 2ME games. So that's where we started. A lot of them were SMS based. So we do things like guess the number of runs in the next, for the next over, for the cricket of this particular match. You'd SMS an answer in, you get a win or a loss on that. Who here has done SMS? Based work or ever worked with SMS infrastructure. There's one word for it. It's horrible and complex. Mostly because of these guys. Because they're nightmares. Especially in our biggest market at that time, which was the subcontinent. So we're working in India and places like that, and where some of the carriers use tin cans and wires. And of course came the smartphone revolution. I myself got involved in that. I was working as a lead developer at CGU, looking after big enterprise systems and writing integration between us and a whole pile of brokers doing brokering systems. And I got in an elevator one day, and 3 people had an iPhone. And I said to myself, I'm out of enterprise. I'm going to mobile. First time ever I'd seen more than one person in the elevator with the same phone was the iPhone. That was a big moment for mobile development. So I made the decision to jump out. I went to places like Learning Planet, I worked with lots in REA where I set up their mobile side of things. Playup moved from a content creator to a content enabler. What do I mean by that? We allowed people to get at content rather than being the primary source of the content. So we curated lots and lots of content into space, put it in the right context, and delivered it to your phone. One of our first places we tried this out was on Facebook. And we very rapidly became one of the top 10 Facebook pages in the world for engagement. Indians love cricket. And we had a cricket thing. And we had over 3 million likes, with a 30 to 40% of those likes being active on any given day. So there's a lot of data coming through our Facebook sync. And it was all manually created. So we knew we could do more, and we could get out in the mobile space. What was that? A bit of a history. So we went through about 9 different versions of the application. I joined the company 2 years ago, after finishing up at REA. And we were just moving into version 1 of our iOS application. We quickly moved through a version 2, version 3. And about this time last year, just through Christmas last year, we started to look at actually how we're bringing data together. And we're doing it really ineffectively. Like most systems, we had lots of SQL tables, we had some Mongo, we had a whole pile of data that was the interconnections was really important in, but all of our interconnections were secondary. So they'd be in joins rather than actually in the data. So I was very, very fortunate. I formerly worked at ThoughtWorks. I worked with a guy by the name of Jim Weather. Jim Weather had just become the chief scientist at Neo4j, and they're a big graph system, and I was on the phone to Jim having a chat to him about various ways of doing this data, and he said, well, why don't you try graph? And I said, all right, give it a swap. Till then, we've been, for the 18 months previous, we've been primarily a Ruby shop. Neo4j is a Java-based platform. My background is Java and Scala. So when we kicked off the graph, we went to a Scala-based system. So why did we go for it? What is Scala? How many people actually have heard of Scala and know what it is? Hey, that's really nice. Scala is a cheesy name. A scalable language is basically where it comes from, right? It's an object-oriented, functional language with seamless Java interoperability. You know what I mean by each of those things? So, it's object-oriented. I have classes and I have behaviours on those classes, or I have things with behaviours on them. Functional means I can compose pieces of execution, put them together and create new pieces of execution. I can do them partially, I can do them completely. I can pass these partially evaluated pieces of information around a system. Very, very handy to be able to do. Seamless Java interoperability is a huge win because there are massive numbers of great Java libraries out there. I mean, half the internet is powered by Java, whether it's stuff, people talking to it from Ruby and talking to things like Elasticsearch or Lucene to get their data out, or whether it's enterprise systems, or Amazon enterprise systems. For us, also importantly, functions were objects. But Scala is just a language, right? And so we needed to build, how would we actually manage that Scala system? And we used a system by the name of Akka. Now, Akka is an actor-based system. So in the same way as Erlang, Akka allows us to send messages between objects that are fully encapsulated. Each actor handles its own state and only its own state, and there is no shared state between actors. And this is really important for scalability and distribution. None of the actors share any state with any other actor. And the only way you can get a piece of information in or out of an actor is send it a message. Okay? And these messages are fully encapsulated, fully serialized. But on top of actors, we add fault tolerance. So Akka is built for let it fail. Actors crash all the time. Well, sometimes. That's pretty good. But the idea is that build the fact that these actors will fail into your system. And so you build a series of supervision. So at the code level, we have things that we have a lot of sports data and we access a lot of sports data. So I'll have an actor that understands the sport data domain. And he'll have tons of actors under, hundreds, thousands of actors underneath it that actually go off and get pieces of information. If one of those actors dies for some reason, couldn't get a piece of HTTP, failed to get whatever, the supervisor's told and he spins up a new one. Right? So the actors, we use an interesting, who's used messaging before, where you've got things like at least once delivery. With actors, you've got at most once delivery. By the way, if you've got any questions along the way, just stick your hand up. I'm quite happy to be interrupted. Third really important thing about Akka is location transparency. You don't know where that actor will execute, and you don't care. Right? And that's really important when you get into scaling, clustering, and think you've just got a virtual mailbox, and you're going to send data to that mailbox. And lastly, something we don't use a lot of, it has these things called transactors. It uses a thing called software transactional memory. So where you do actually have to have a cache or something like that, you can use software transactional memory to treat it a little bit like a database. You try your operations, if they fail, they'll get rerun. Right? So if two things try to write the same piece of memory, one of the things will be thrown out, another one will get it. The third piece of the problem, as I kind of mentioned before, was Neo4j. Now Neo4j is a graph database. And what that means is rather than storing your tables and rows, what we have are vertices and edges. So vertices is something and an edge is connection. So we have millions, literally, tens of millions of these vertices with edge connections. Some of those having up to 10,000 edge connections. So that's how we connect our data. Each of the vertices or edges can have some properties on it. So if we want to store a string against a particular vertex, it's like a property. So think of it as a very simple document object model, or even each vertex being a row from a database. It's just a list of properties. Neo4j itself is completely untyped, so it doesn't actually express anything over the top of your model. You have to do that yourself. And lastly, it has full text index. So we can, it's got a Lucene index underneath, so we can go and put various parts of that information into the Lucene indexes, and we've got our own analyzers for certain types of things to do different types of stop wording. And when you've got when you actually want to do auto completion for English and Chinese because they're multilingual, you actually need different rules for how you tokenize the text and store the text. So we have our own insistence. I'm going to take this slide out because I've noticed there isn't a whiteboard. So I was just going to draw quickly how this comes in here. But let's not worry about it too much. So here I've got the actors written in Scala, looking at the graph database. So what do we have? Where do we run all this? Well, like a lot of startups are inside of AWS. We run in, our production runs out of one zone at the moment, primarily, of the graph, which is US West. A lot of our traffic is out of the US, so we use US West. Our graph server runs a really big M2 2XL, mostly because we want a lot of memory. We use a lot of memory. We actually don't need the CPU, but we do need the memory. And the graph server is based on Ubuntu 13.04 with a JRE7 stuck on top. The JVM, we have an 8 gig heap for the graph. And I think we've got 32 gig on that box, thereabouts, some massive amount. I'll show you how we use that in a sec. We've got a bunch of other JVM processors on there. They get about 128 meg to a gig each. They're not really heavy. They've got plenty of memory. And we use parallel garbage collection because we are creating literally tens of thousands of objects a second when we've got a lot of queries coming through. Because these messages, for every message, we're going to create an object, we're going to serialize it over the network, we're going to drop it, we're going to create a bunch of things. So we use a lot of garbage collection. It's mostly in very, very early generations. We get very little pushing up to the later generations, which is happening. And the remaining memory is reserved for system cache and memory map buffers. So we do a bunch of memory mapping to bring the graph into memory. So we page it in and out. And so what we want is the system to have a lot of memory in which to bring the file system, as much of the file system up to the memory level. And we do a few tricks with our file system with multiple stripes on our elastic storage. So we get a 10 gig slice and then we put another 10 gig slice on a 10 gig slice. It actually means that it ends up getting sliced across a whole pile of, you get better parallel reads out of AWS. So building. So now we've got some runtime stuff, got what we want. So how do we go about building it? So we use in Scala language, just like guys were using Maven, I think I mentioned Maven before, we use a thing called SBT. SBT is the Scala equivalent of Maven or Ant. And its responsibility is to basically build a bunch of jars. And it does things like compile ls and CSS and does our HTML optimization, JavaScript optimization, and runs closure on the JavaScript to tighten it up, and it does a bunch of other things. We then build a bunch of Debian packages. Right? And our Debian packages basically build things that put our binaries into opt, add an upstart file for the, whatever it happens to be, graph server, the HTTP server, etc. And sets the basic permissions on the data and log directories. Upstart's a really, really easy version. I don't know, I'm back from the day where you had to write rc.md files, which was just getting horrible. That is the upstart file we use to boot our graph server. And it's only so long because I have to break the lines a number of times. Our jars are runnable, so we build runnable jars and we just execute them with the VM. We use parallel garbage collection sets up. Debian package, you've got to make a choice about what your configuration is going to be. It's going to write some stuff to etc. So by default, we write everything inside of Debian packages as if it's going to production. Because then you don't end up with the bit of dev left in the production version. And then we bake AMIs from all of that. So we build these Debian packages and we start to bake AMIs out of it. Now I touched on this last meeting, I showed some very quick stuff in the lightning talk around Packer. So we use a tool called Packer, packer.io, same guys who do Vagrant, which is also a very, very handy tool. And what it does is it creates machine images for multiple platforms, and we use it for 2, from a single config. So we can configure the build out of our images for both our local Vagrant or / VirtualBox builds and our AMI builds from exactly the same file, with some small tweaks here and there as far as the configuration of the individual box, such as how much memory you're going to put onto that box, what type of AMI you're going to use for the specific part. And some things I'll show you in a moment about some of the customization you have to do between different types of images. The things you want to do on Vagrant you don't want to do on AMIs, vice versa. Images have a pile of benefits. I don't know how many people are still tending their servers. We used to tend our servers, look after them. Now we don't, we just shoot them in the head when they're done. A bit more like cable. They allow us to do fast deployment. Previously it was taking us up to 15 minutes to deploy a server. When you're responding to load with an auto-scale event, well, the loads are gone in 15 minutes. You're lucky if it's not gone in 30 seconds, right? Especially if you're responding to load based off an ad or something like that. So, which was ridiculous for us. They provide you a nice, stable thing to launch. There's no difference between any of the machines. You're guaranteed that if I run this AMI and this AMI, they're the same. They've got exactly the same code on it. They're exactly the same AMI. I have exactly the same thing deployed. I don't have to go, did that thing did that puppet one fail and then didn't do that and now it doesn't have it? It's just horrible. Testability. We can run those AMIs up, hammer them as much as we like. We do a lot of our testing with load scripts. So we've got our load scripts are sort of smart user scripts. And we use a tool called Locust. We run up a Locust farm, and then it starts talking to, we're a hypermedia-based API, so it just starts walking our APIs and talking to bits, and it knows how to authenticate itself and things like that, and starts doing a bunch of stuff like that. Nice part is when we're working on scripts, we can run up a little environment. The guy can work on his scripts. He just runs up the environment, shuts it down. Right? And it's guaranteed that same AMI that he's using there is going to be the one I'm going to put into staging, and if it is all successful, the one I'm going to put into production. So, Packer makes creating images a breeze. Prior to Packer, creating images was a pain in the butt. For me anyway, because it's not my full-time gig. So let me show you a little bit of an example of our Packer file. I'm going to start with things called builders. See, Packer file really has 3 parts to it. Builders, provisioners, and variables. The builders, in this case, is going to build on Amazon. And I'm saying for the build, give me a T1 micro. I'm going to build the image with a T1 micro up in Sydney. Use this AMI as your base AMI. So we pick one of the base AMIs from Amazon, and it's actually one of the base Ubuntu AMIs. And then I'm going to build, and when you finish building this thing, put some extra Amazon data onto it, which is really handy. So give the resultant AMI a specific name, and we put a user version string in there and a timestamp. But you can put other things in, such as your Git hash and things like that to actually say where it came from. Timestamp's usually enough for us. And you can set, which is very handy, things like tags, which you can then later read in your cloud init scripts and cloud formation, which is also a kind of handy thing to be able to do. And lastly, after you finish building the AMI and sitting in Sydney, take a copy of that AMI and go and stick it in US West, because that's actually where I'm going to deploy things from. I don't actually deploy them in Sydney, but I want that AMI over in US West. And I've written that in a couple of configs. Now, if you notice, here I use a couple of variables. There's some built-in ones, which is timestamp, ISO time, things like that. And then there's also user ones. And user ones, you can either pass on the command line, or you can have them built in, depending on how you're using them. So you can put default values in here, and then you put a -var when you call packer to step it out. So variables allow you to put in things like, we use it for development versions, we use it for tags and things like that. But just gives us a name for a version in this case. The last part of the puzzle is a thing called provisioners. So I've got this AMI, I've launched it, I've got a base thing, it's sitting up in there, now I actually have to put stuff on it. It supports a few provisioners. The first one is your good old shell script. So in our case, our shell script will do things like, what's the first one doing? Make sure the thing's all up to date. As far as packages are concerned, we go and pull all the latest packages. That's a little script that does that. We install Puppet. I'll talk to you a little bit about how we use Puppet in production later. It goes off and installs, we've got it on there for installing spot packages, and then this build date thing pulls some data in and stamps the, so if you're ever on the IM, you can go in and go, well, when was this freaking AMI actually built? Oh yeah, and it puts some actual build information in there, so that little script at the end. This one's kind of handy. So you've got this other provision which is type file. And that will read a local directory called packages and copy it to /10. Right? Let's SCP it up to 10. So our Debian packages get built, they get stuck in this local package directory, and then they get copied to /10. After that's run, then we run our install and spot packages. So we go and depackage -i and install all those things, and away it goes. Whoops. And lastly, we have our Puppet configuration. So there's a lot of things that Puppet's great for, which is, as far as, managing what permissions are there and all those sort of things. We like to, we have a lot of pattern-based Puppet stuff we want to run. And we also use it for detecting when certain pre-provisioned files have changed. There's problems with the default config you get out of the JDK when you drop in, as far as security and key generation and things like that go. So we have a specific patch to patch that. That's part of our build and part of the Puppet install, and we detect whether the original file has changed such that we need to go and have a look at it before you can actually go any further. And so we run a masterless Puppet just to go off and do all your basic machine configuration, add users, do all those sort of wonderful things. Everything I showed you there was common to all providers. But at times, especially we use it mostly with Vagrant, you want to do a specific thing for a specific type of provider. For instance, with VirtualBox, we want to install the Vagrant tools, and we also want to add the guest editions, because it lets us do some syncing up locally on the file systems. So that's just a matter of saying only run this or for these builders. So that provision will only run for that set of builders. Very, very handy. And then you just run packet build. In this case, I'm saying only do the AWS build. It will actually, if you've got an AWS build, a Vagrant build, a VMware build, we support a couple of others. If you've got all those configured, it will actually build them all in parallel. So you get a Vagrant build going on, a VirtualBox build going on at the same time as your VMware Fusion build or your VMware build and your AMI build. It will just build them all in parallel. This just says, don't bother about the vagrant build, I just want an AWS build. Oops, and a few shiny minutes, you have a nice new shiny image. So it's the simplest way I know of building an image. And these images are, our images are 99.9% ready for production. Right? Very little we have to do at runtime to actually do final configuration. We do a little bit of final configuration. We have a CI system, and we inject a couple of extra things from the CI into those variable spaces. So source AMI, so we've got a CI in US West, as well as in Sydney. So it means that when I'm building in US West, it goes the right AMI, does some things like that, which is really handy, because the time, the packages we build about 200 mega packages. The actual copying of those packages can take 10 minutes. If we've got the thing sitting in US West, it's faster for me to build the bloody thing in US West and deploy it from there than it is to copy the packages to US West. So I've got a slide next. I can't remember why I had it there. Yeah, I can't remember. So I mentioned before that the baked configuration, it should be baked, not backed, config is for production. Now we obviously run dev environments and we run staging environments. And we use basically Cloud script to take care of that. It has the basic minimum stuff. To pretty much the only place we write is etc Playup. So it's going to overwrite some etc files. Or apply some patches or diffs on some etc files, depending on the way we go. The other thing it does is it configures a local Puppet master. Now, we don't use much live Puppet in the new infrastructure. In our old infrastructure, it was all live Puppet driven. So we would upgrade packages by changing Puppet script and pushing it out. Very little of our the new infrastructure is Puppet driven. What we do use Puppet for is if we want to push out something, we've got a hot fix that we have to push out really quickly. We don't want to bring things up and do the migration. Puppet's there, it's very handy for being able to do that. If we want to rotate security keys, Puppet's there, we can push it in, push out to all the machines the security keys. So we use a little bit of Puppet, but it's mostly for doing a couple of ad hoc things as opposed to, or interim things, as opposed to how we manage our infrastructure. We have lots of CloudFormation scripts, which are just, I did come across a really nice DSL for CloudFormation last week, which I'm getting rid of all our CloudFormation scripts and rewriting them in Python, and it's like gone from me to the door in length for some of these to a page I can read. So it's really nice because I can just import, I can actually do things like import and write functions that actually generate the bits. So it's really, really handy. But our CloudFormation scripts basically control which image we're going to boot, what cloud net values we're going to stick in from tags. That's not a perfect world. We still deal with a few challenges. And by a few, way too many we could talk about. One of our biggest ones is persistent data. Our graph has a whole pile of persistent data, and when we bring up an image, we've got to get that persistent data to the new version of the graph. And so we've got various ways of doing that. We're experimenting with different ways of doing it. We're working with ZFS and snapshots on ZFS. And so basically interrupting at the end of a write, taking ZFS snap, and then letting the next write go through. So we can then take that snap and push it aside. We can put our systems into read-only mode, which is kind of handy. So we use the actors to actually move rather than going to the graph. We go and say, no, just hang on to that information for a while we do something, and it'll handle it. And works fine for writes. Reads, we kind of need to be there 99.9999% of the time. The second one is service registration, so knowing where other bits of the graph things are. That's not dynamic at the moment. We use internally a bunch of CNAMEs to point between things, and then we go and update our Route 53 files via the CloudFormation scripts to do those things. Probably like something that was a bit more, a little more dynamic, that actually didn't rely on DNS for doing some of this sort of stuff. Cluster membership, we run our Acker things up into clusters. Acker at the moment requires a master, a couple of well-known hosts, and then you can add to it. We still haven't got that the way I'd like it. We still have to say, through some CNAMEs, here these things. So we're working on those sort of things. We're actively looking at 2 technologies at the moment to help us with some of these. Syncing up is spin up time. So we can spin a server up in about 30 to 45 seconds now, which is pretty good compared to 15 minutes. I'd like to get that down to 5 to 10 seconds. And that's where we think Docker might come in. So what we do is we have a whole pile of blank template boxes, which actually have all of our software available to them, and then we run up Docker instances. So we build an image that has all the bits we need, and then I can run up whatever Docker containers I need on that box at any given time. So the boxes become a little dumber and less about what they are, and then Docker actually handles what we're doing at that level. And the second one is Apache Mesos, which is a sort of an operating system that sits above these sort of things. You have to configure your things to talk. All right, small little club. Come join us. We're doing some interesting things specifically in the journalism space. We, about 6 months ago, took on a head of editorial. He's the head editor for The Age score. He now runs our editorial team, and journalists are being fired all over the world, right? There's no journalists left, right? And because of the traditional way that a journalist delivers their information, the journalist is bound to be captured inside of this, inside of a publication or something like that, and they're pitching against the publication. So we give them a way of going directly to the consumer. There are a lot of great sports journalists who have very specific relationships with teams. We have a guy from Barcelona who is all the Barcelona training things. He has close to 1 million Twitter followers, something ridiculous, because he tweets something from a photo of somebody, falling over at a training session. All these Spanish guys go, wow! They're pretty fanatical about that. We're being very cautious in our hiring. In past, Playup hasn't been. We've hired a lot of people very quickly. We now spend a lot of time hiring, and if you're interested, talk to myself or Andrea. I'm going to leave you with one really important thing. That you will miss 100% of the shots you do not take. So it is worth trying to do some of these things and make things better, because what's the worst that can happen? You fail. Well, if you didn't do it, you failed. So trying some of these things out and trying to do something different in an environment is a really important thing that we sort of think. Questions?
Yeah, I'm just wondering, for your dedicated graph database,
Yep.
Is there a kind of constant performance advantage, or are there particular things that it does which you just couldn't do with representing a graph in a relational database?
Yeah, so that's a good question. Graph database allows us to make the connections between information first-class citizens. Now, when those connections are first-class citizens, your ability to move between connections becomes A, powerfully expressive, and B, incredibly fast. I'll give you an example. We so our first version of the graph we did would work great for aggregated content. In fact, we had the opposite problem most people have. Normally when you start aggregating a bunch of things get slower. We actually got faster. The more you wanted information from disparate sources, the faster we got. The problem is, if you got information from one source that didn't have much information, it got really slow. And so we were able to add a few edges to that and take that from a tens of seconds operation on the worst things down to a tens of milliseconds operation. It involved no indexes. It involved no, like trying to figure out, create a new table and put a new join in and all those sort of things. It was just a matter of adding a new edge relationship in. We ran a quick migration. The migration took 20 minutes, inferred all the edges across the graph, and suddenly the thing was, several orders of magnitude faster. The thing with a graph database is adding new connections between information is trivial. And in our industry, connections between information is really important. We have a whole pile of stuff to do with energy and resistance. So let's say a goal has been scored in a match. Now, and nobody said anything about it or thinks anything of it. Well, that's not going to have much in the way of energy. But let's say it's scored in the last minute of the final, then that's going to have a certain amount of more energy coming in, and that will push itself, the number of edges you're allowed to traverse to get to that information will go up. Things like that are really, really easy to do with graph theory, right? Because we can do shortest path, we can do lowest weights, all these sort of things. Really well understood mathematics on this stuff. So walking these edges and vertices is really well understood. And then, which would just be a nightmare in a relational database. Like you'd end up with 400 joins and 20 minutes later you have your answer, and we want to be out in milliseconds. So we have a performance guideline of we want to be last byte in, first byte out within 500 milliseconds. Is kind of, yeah, okay. 200 milliseconds is where we want to be. I've later been grumpy when I've been seeing the third digit. Right, so most of our graph operations happen in the sub 100 millisecond. We're last byte of the HCP in to first byte out within, which is real data, within 100 milliseconds. Formerly, especially when we were using Ruby, we relied on caching. Now, caching is great if you have everybody consuming the same piece of information. But as we're adding personalization, pretty much every request becomes a calculation. So we have to be fast. We have to be really fast. And the graph is a really, really fast way for us to do that. We tried a bunch of other things. We're using Neo4j at the moment. Neo4j is great at scaling vertically, but not so good at horizontal. Ends up with a master-slave reader-writer. We're also experimenting with a technology called Titan, which sits on top of Cassandra. And we use Cassandra for some of our, already use Cassandra for some of our logging and things like that. It will allow us to do some of the distribution we want to do. It slows down the mean time a little bit, but the distributed aspect means I can go and put a server in Europe, a server in Singapore, a server in thing, and have them all replicate between each other, which is quite nice.
What's your striping setup on the database?
Can
you go into that a little bit more?
So it's actually not much of a striping setup. What we do is when we allocate the volume, you allocate the volume as like a 10 gig volume, and then you go and add another 10 gig to it, another 10 gig to it, another 10 gig to it, and you effectively get striping at the lowest level. And then we use the like ZFS or something above that to actually join those partitions together to give us one value. We're very sensitive to being, we memory map. So Neo does a lot of memory mapping. So we're very sensitive to anything that impedes that ability to memory map, which is why we keep a pile of memory aside for the memory map files. So we just make sure we've got a pile of that. Once a graph is warm, it's pretty much sitting in memory. The only time we need the striping in disk is when we're writing. Now, our read to write operations is hundreds to one.
You mentioned Docker.
Yeah.
Are you looking at Core OS instead of Apache Mesos for that?
Not yet. So we're just investigating some of these things. So we're looking at Mesos because of its integration with Docker. But yeah, we'll be looking at various parts. I mean, the Akka side of things, we're running a small Akka cluster. We're on 2.2 with experimental stuff in 2.3. It is the easiest way to write software once you sort of get your head around messaging. We made some mistakes early on. We sort of treated our actors as message queues, and so we had a few actors. Now we've got tens of thousands of actors, where each actor is responsible for one piece of data. We'll have an actor that's responsible for the current score in a match. We'll have an actor that's responsible for the list of competitions the team plays in. Right? And we just proliferate actors because then they just own one piece of data. Messaging between actors is lightning fast, so yeah. And that's, it's one of the things we're actually using a lot more is using these actors to spread information out, do caching, they can be smart. We're moving, next year we'll actually move to event source information out to the client. So our clients at the moment, strangely enough, are actually poll-based. It's actually the most effective way of us doing some of this stuff. It's actually be poll. Mobile applications are notoriously bad for staying connected, right? If you're constantly getting disconnected. So anything that's using like, first version of the application we did use XMPP before I joined. It was a freaking nightmare. It spent all of its time reconnecting to the XMPP server and getting the list of friends. That was all that was going across the network. Because you move around on mobile, you drop your connection all the time. So we ended up with HTTP polling. We do some things. I've got another talk I did for Yale this year for their nights about how we use the hypermedia stuff and how we control our polling and tell the client how often to poll back. We do some standard HTTP stuff to actually control them and put back pressure onto the client to stop them being as hard. But, any other questions? All right, well, thank you very much.
So the pizza's here, it's been here for a while. We'll just quickly go around the room and do what we normally do with available jobs. Either you're looking for work or you have a position available. Anyone?
So never hiring, so come chat to us too.
Looking for anyone particular? Just anyone?
Someone within my team, so some DevOps practice, some CV, engineering type skills. So just having type skills.
Anyone else? This is strange.
Kinda looking myself, Linux system engineer, absolutely don't mind DevOps at all, actually would like to do something more like that, but I don't really have the skill set yet. Been doing that job for roughly 15 years now, so I've seen quite a lot of stuff. So whatever I don't know, I can easily learn.
Where's Jeff? He's always here.
He's still looking.
Anyone
All right,
else?
so these sessions only work when people volunteer their time to do presentations, so thanks to those people. And also thanks to the hosts who provide pizza and beer and the venue. So we're going to talk about next month.
Yeah, next month is our social sort of meetup because it's pretty close to holidays. Usually we go to a bar. So we're going to Beer Deluxe on the 17th of December, which is kind of not the second Tuesday, but it's closer to Christmas. So yeah, Red Guava, the company I work for, is actually helping with a round of drinks. So hopefully see you all there. 17th of December. Third Tuesday, I think. So, yeah.
Cool. And next year we'll be looking for other people to host us and other people to talk. So thanks for coming tonight, and let's eat pizza. Right.
Thank you.